Hello there. So let's take a look at equilibrium chemistry now, our last big section for chapter 6. And think about a journey that you'd be going on, maybe a journey on holiday before coming back. And you've got that journey out to your destination. Let's say the destination is Orlando and your departure point is Carterville. That's just one half of the journey, of course. And then there's a journey back from Orlando back to Carterville, where the roles have changed. Now, Orlando is your departure point, and Carterville is your arrival point, your destination. So if somebody were to phone you during that holiday period, and you said you were in Orlando, you would need to clarify whether you've been driving to Orlando on the first half of the journey, or you're about to drive back to Carterville on the second half of the journey, because your journey is a two-way street, a journey in two directions. And that's kind of like what we have with these reversible systems. There's two halves to the tail, two sides to the coin. And so we've got a normal interpretation from left to right for the reaction, where the N2O4 is our starting material that's going to be used up and turned into the product NO2, nitrogen dioxide. But nitrogen dioxide, as it builds in yield, those molecules undergo collisions, and those collisions can cause the bonds to break, and the molecules, if you like, unravel back into the starting material, N2O4. So there's a separate reaction, a separate right to left reaction, which we call the back reaction. And we'll be talking about this a lot for the rest of the chapter 6. When we're talking about the reaction from left to right, that's the forward reaction. But the separate reaction from right to left is the back reaction. We're using the same chemicals, but now their role in the reaction has been completely reversed. Now the nitrogen dioxide is the reactant being used up. And now the N2O4, the dinitrogen tetroxide, now it's the product in that back reaction. So normally we represent the chemical reaction with these two arrows, each arrow with just half a head, because it's just half the story, but it's setting up this two-way street of traffic. N2O4 turning into NO2, and NO2 turning into N2O4. Two separate reactions which are like the flip side to the same coin. So what happens with these reactions? Well, I'm glad you asked. So let's say we start and we pour a chemical into the reaction flask here. So we just pour in a bottle of N2O4, and those molecules with kinetic energy in solution whiz around and they collide with each other. They collide and sometimes break their bonds to form two molecules of nitrogen dioxide. So after the first couple of minutes, as we look at the concentration of the two sets of materials, we've used up a tiny bit of the N2O4 so that we can produce a tiny bit of the NO2, which of course is a product in the product in the forward reaction, I beg your pardon. If we let more time pass, the reaction continues, and so more of the N2O4 has been turned into NO2. So the concentration of the N2O4 continues to decline, as we said in collision theory on Wednesday. The more successful a reaction is, the more a victim of its own success it becomes as we use up that material and we produce more of its product, the NO2. So let's say we leave the reaction for a good hour. And so we can see that continued decline in the concentration of the N2O4 as it's being used up in the forward reaction, and an increase in the production of the NO2 because that's a product of the forward reaction. But you can see how the rapid increase and the rapid decrease of these two chemicals is starting to peter out. We're getting close to the amount of chemical plateauing out or becoming constant. That's because the opposing back reaction, which uses up this chemical, the NO2, is starting to take hold, and it's turning this chemical back into the original N2O4. So that's why it's not being depleted as quickly, and that's why the concentration of the NO2 isn't increasing as quickly as it was at the beginning. If we leave the reaction a little bit longer, we will eventually reach this point where the concentration of each material completely flatlines and no longer changes. Now, the particular concentration of those two materials could vary depending on how much of the material we had, what temperature is, what the pressure is. But somewhere along this axis, we will see it plateau out. Maybe we still finish up with more N2O4, or maybe we finish with even less than the graph suggests. Depends on the conditions. But the graph does plateau out. The concentrations of all chemicals no longer change. And that's because we've reached a very important point in this reversible system. And that is that the rate of the forward reaction is equal to the rate of the back reaction. So the N2O4, which is being used up by the forward reaction, is also being produced by the back reaction. N2O4 turning into NO2, but the back reaction uses up NO2 to reproduce N2O4. So as one reaction uses a chemical up, the other reaction reproduces it. And that's why the concentrations no longer change. The rate of the two competing reactions is equal. And so we've reached a state of equilibrium, or dynamic equilibrium, as it's called. And we can see that when we look at a graph of the rates of the two reactions. Remember, we started off with the N2O4, which is a chemical for the forward reaction, but it starts to get used up, and so the rate of the reaction starts to slow down. We produce a chemical that drives the back reaction, NO2, and so the rate of that reaction starts to speed up. And we reach this dynamic point of equilibrium where the two reactions are now happening at the exact same rate. And so concentration of each chemical no longer changes. It doesn't mean that the concentrations are equal, it just means that they no longer change. Think of it like an analogy would be, I think my analogy in the next page actually is two people trying to bail water out of their boat, and they just happen to be alongside each other. One guy bails water out of his boat into the other guy's boat. Another guy just as quickly bails water out of his boat into the first guy's boat. If they're working at the same rate, the amount of water in each boat no longer changes because a bucket of water is on the way out as quickly as a bucket of water is on the way in. This is what we mean by this dynamic equilibrium. So we need to learn to understand how the reaction responds when these changes happen. So let's take a look at an example. This is NaCl, nitrosyl chloride, which turns into nitric oxide and chlorine in the forward reaction. But there's a competing back reaction which combines nitric oxide and chlorine and turns it into nitrosyl chloride. So name the product of the back reaction. As we'd said earlier, the back reaction runs from right to left. So this is where we're starting. This is always the starting point of the back reaction, and these are the chemicals which are being used up in the back reaction. We follow the path of the back reaction, And this is our endpoint. That's what's being produced by the back reaction. In this case, the nitrosyl chloride. So primary product, nitrosyl chloride. Let me create a little bit more space for myself here. So I get all the questions on the page. There we go, that looks better. Next question, name the reactants of the forward reaction. Again, the forward reaction is from left to right. This is what we're starting off with now. And we're starting off with the nitrosyl chloride. So we see how each reaction is the flip side of the same coin. Nitrosyl chloride can be the reactant or product depending on which direction, which reaction we're talking about. Left to right is the forward, right to left is the back. Now, you're then told that the solution suddenly becomes red in color. Which reaction is working harder? So we're assuming that either something has disturbed equilibrium or we're looking at the reaction before equilibrium is established. Remember, the reactions go back and forth for a while before we reach equilibrium. And once we do, we normally don't see concentrations changing. But until we reach it, there is one of the two reactions which has the upper hand. And so if the solution becomes red, we ask ourselves, which chemical is red in color? Well, of course, that's the nitrosyl chloride. And for it to become red in color, the solution, we must be producing more of the nitrosyl chloride. And the reaction that does that is the back reaction. We use up NO and Cl2 and turn it into NOCl. So the back reaction is working harder. We can say that equilibrium is moving to the left. Which is effectively saying that the back reaction is working harder, it's producing its product, or we say that the back reaction is favored. That's all we mean when we talk about a reaction being favored. That reaction is working harder than the other competing reaction. And so when the back reaction works harder, it produces more of its product, and so that gives a more intense color. What happens to the concentrations? Well, of course, the nitrosyl chloride is a product of the back reaction. So that concentration would be increasing as the color intensity of red increases. The nitric oxide and the chlorine, on the other hand, are the chemicals being used up by the back reaction. So their concentrations would be expected to decrease. Next one, the rate of a bubbling yellow gas is observed to speed up. What's happening now? So seeing that gas, that yellow gas being produced, that's the observation. That's the reaction of the system. And the only way to produce this chlorine gas is to get the forward reaction to work harder. So this is all about the forward reaction working harder. Because that's a movement from left to right. And so we sometimes say that the forward reaction is favored. Whenever the forward reaction starts producing more of its products, in this case nitric oxide and chlorine, we say that the forward reaction is favored. So of course we have to use up nitrosyl chloride in the forward reaction to get it going, but we'll increase the concentration of the nitric oxide and the chlorine. When we're talking about the forward reaction, we're moving from left to right, using up the chemicals on the left, producing the chemicals on the right. When we're talking about the back reaction, we're talking about a movement from right to left, using up the chemicals on the right, producing the chemicals on the left. That's where the back reaction is heading. Okay, let's see what we've got next. So it's important to understand where the position of equilibrium is. Do we have mostly the products of the forward reaction, or do we have the initial reactants in high concentration, which should be the products for the back reaction? Where does equilibrium lie? Because many of these reversible systems which reach equilibrium, we have pharmaceutical companies depending on being able to produce just one set of products in high quantity. And so we need to know where equilibrium is and how much of each chemical we have, roughly, if we're going to manipulate the system to producing more. So we calculate what we call the equilibrium constant, or K as it's known, and we look at the reaction using this genetic example here. We look at the reaction as we normally would do from left to right, where chemical A and B with their molar coefficients of A and B are the starting reactants, and chemicals C and D with their molar coefficients C and D are the products of the forward reaction. So we're going to sample at equilibrium the concentration of each chemical, and we multiply together the concentration of the products C and D on the right, divided by the concentration of the reactants A and B as they stand at equilibrium. And each chemical uses its molar coefficient from the equation as a power. So the concentration of C taken to the number of moles that we had in the equation, concentration of D in parentheses, that's what these square parentheses are for, to anoint a concentration. A concentration taken to the number of moles of D, and the concentration of A taken to the number of moles of A from the equation, and so on. Now, if we use an actual reaction as an example, whoops, a bit jumpy, my Word document here. Look at our example. Carbon monoxide combusted in oxygen to produce carbon dioxide. The concentrations, by the way, would be in molarity, moles per litre. We haven't done calculations for molarity yet. We'll come back and look at that in chapter 8. So the total moles of that solute, that chemical, divided by the volume in litres, presumably of water, the solvent, gives us the concentration. So for the setup, it's the concentration of carbon dioxide divided by the concentration of the reactants, CO and O2. We take the carbon monoxide concentration to the power of 2 because there's 2 moles in the equation. And we take the carbon dioxide concentration to the power of 2 because, again, there's 2 moles in the equation. Excuse me. So let's think about what a value would mean for us and how we'd interpret it. If the value from those concentrations was close to 1, that means we've got almost an equal quantity of reactants and products. So neither reaction is favoured. That's a real nightmare scenario for pharmaceutical companies. A 50-50 split. The closer you are to 1, the closer you are to that 50-50 split. However, if you had mostly the reactants compared to the products, we would get a value much less than 1. Because remember, it's the products divided by the concentration of the reactants. So if it's a bottom-heavy calculation, we get a very small value. If it was virtually all the initial reactants, it'd be something like 10 to the power of minus 6, the value. So when that happens, it means that the reaction working harder before equilibrium was established was the reaction producing those starting materials. That's the products from the back reaction, as we read it from right to left. And so when the K value is small, less than 1, we say that the back reaction is favored, or we say that equilibrium is on the right. Sorry, equilibrium is on the left, I beg your pardon. The last possibility is that we've actually got mostly products and very little of the initial reactants. Of course, for this to happen, it must be that the forward reaction was working harder before equilibrium was established. Remember, once we establish equilibrium, the two reactions are working at the same rate, and so the concentrations of each chemical no longer changes. So for the K value to be greater than 1, we've got most of the products of the forward reaction. We say that equilibrium is on the right, or we say that the forward reaction is favored. Now, when we're setting up that calculation for the equilibrium constant, there's just two caveats that we have to be aware of. Two things that we look for, which we would ignore when doing the calculation. The first one is the presence of water in the reaction when we have aqueous conditions. When we talk about aqueous conditions, we're talking about chemicals in the reaction, like cyanide, having water added to them to make an aqueous solution. That's what we mean by aqueous, a chemical dissolved in water. So chemicals like the cyanide and the hydrogen cyanide, those chemicals, before the reaction even starts, were already flooded, dissolved in water to make a solution. And so the fact that this reaction either uses up water in the forward reaction or produces water in the back reaction isn't really going to have a dramatic effect on the concentration of water in the solution, because we already had lots of water by dissolving those chemicals in water. So that water which is produced or used is insignificant compared to the total concentration of water in the system. Why? All right, somebody interested in my Fitbit there. So if water is part of the reaction, but any of the other chemicals are aqueous, as it happens with this one, all of the other chemicals are aqueous, but we'd only need one. We would then ignore water when we write the equilibrium expression. We'll look at some examples shortly. The main examples where we do include water are when the reaction is carried out at a high temperature, because then of course the water will boil. So you'll see water and other chemicals written with a G, because it's in the gas state. There's a terrible hash of it there.
I'm daddy now.
You're daddy? Okay. Who am I then?
Your brother.
Okay. So if you see water written as a gas state, that's usually a pretty big clue that you will include water in your equilibrium expression. Okay, so that's the first one, water. The other caveat to all this, when writing the equilibrium expression, is to ignore the presence of solids. Solids cannot have their concentration measured, like say ammonium chloride here. Can't measure it. You can measure its mass, you can measure its volume, so you can therefore take its density, but you cannot, excuse me, who's the daddy here? Right, to bribe her with a Twizzler. Okay, so we ignore water if there's aqueous conditions, and we ignore solids. You can't take the concentration of a solid. So writing the expression, that would be the products of the forward reaction divided by the reactants, but the reactant is a solid, so it's all over 1, and anything divided by 1 is exactly the same thing. So the equilibrium expression comes to the concentration of ammonium ions multiplied by the concentration of the chloride ions. Let's look at some other examples. Calcium carbonate. Again, we check first, we're looking for water in aqueous conditions and looking for solids. We actually have two solids, calcium carbonate and the calcium oxide. So products divided by reactants, it just comes down to the CO2 concentration. As that concentration increases, equilibrium is moving to the right. The forward reaction is favored. As the concentration decreases, then we're moving to the left. The back reaction is favored. Next one, the N2O4 decomposing into the NO2, as we saw our first example. Writing the equilibrium expression for that, that'd be the NO2 concentration to the power of 2, because there's 2 moles in the equation, divided by the concentration of the N2O4. Again, the square parentheses imply that there's a concentration value for that particular chemical to be added. The bromine pentafluoride decomposing into bromine and fluorine. So the products, that's bromine and fluorine, we multiply them together with the fluorine taken to the power of 5 because there's 5 moles in the equation, divided by the concentration of the bromopentafluoride taken to the power of 2 because there's 2 moles in the equation. So we'd be ready to calculate that equilibrium constant if we had some values, and I would have to provide those values for you. Here's one more, but take a second, pause the video, and work this one out for yourself. How would the equilibrium expression be written as we try and calculate the equilibrium constant and therefore the position of equilibrium? Okay, I'll assume we're back. For those of you who did it, always worth taking a try at these things. Don't just wait for me to tell you. Because for that K value, it's the combined concentration of the products from the point of view of the forward reaction divided by the combined concentration of those initial ingredients from the point of view of the forward reaction. So we've got calcium carbonate, that's a solid. We're going to ignore that. And we also have water, which therefore gives us a question mark. Do we use it or ignore it? Well, we've got carbon dioxide, the hydrogen carbonate, and the calcium ions, all in aqueous conditions. These chemicals are being mixed into water to form solutions, and then we've poured those solutions together. So if the reaction happens to use up or produce some water, that's insignificant compared to all the water we use to initially mix those chemicals. So the concentration effectively doesn't change, and we incorporate it into the equilibrium expression. So for those products, that would be the CO2, because we're ignoring the water. So the carbon dioxide concentration divided by, now I've got a cat attacking me. Carbon dioxide concentration divided by the concentration of calcium ions multiplied with the concentration of hydrogen carbonate. Taken to the power of 2 because there's 2 moles in the equilibrium reaction. So having worked out the expression, when provided with values for the concentration of these chemicals, we could work out the equilibrium constant itself. Okay, I think that's pretty close to where we were on Friday, yes. So what we're going to start with on Monday, either on campus at 11 a.m. or later on with our online lecture, we're going to start with a couple of extra examples, but this time with concentrations provided, so we can work out the equilibrium constant and interpret it before we start looking at Le Chatelier's principle, probably looking at catalysts and adding or removing chemicals from the system. Okay, that's all from me and my cat. Stay safe, wash your hands, wear that mask.